Javaloyes from University of Murcia, and before he start his talk, we are going to present to give him a small gift from the organizing committees.
I would like to begin by thanking the scientific committee, the organizers, for giving me the opportunity to stay here in this Congress. It's a very special meeting for me because I've spent several years in Brazil, and it was really a very nice experience. I think that in general, Brazilian people are very friendly, and this is something that is very nice for the day-to-day. You go there to the department, you cross someone, and you chat a little bit, and this is something really nice. So I encourage you to continue with your Brazilian style. So, and also I want to thank the organizers because it's everything very nice. They have done a very good job. So I'm going to begin with a problem, with a Zermelo problem of navigation. And well, imagine that you want to cross the Amazon River, okay? Well, if you want to cross the Amazon River, but you want to cross it in the shortest time, in a path that takes the shortest time possible. So, well, you have to take into account that there is a, well, in principle, you are going to cross the river with a motorboat that has an engine, and well, the power of the engine allows you to cross in a maximum speed. But then you have the help of the current or the stream of the river. So you have to add the engine, the power of the engine, to the current of the river. That sometimes the current of the river can be positive or negative. So the question is, which is the path that it is the shortest path in time? Okay, because, well, with this configuration, we have determined the velocity, the speed in every direction. So if you choose a path, you can compute the time, okay? And then the question is, if you consider all the possible paths between one side of the river, or between one point and the other, which is the one which is the shortest time? Probably, well, you have to take into account that in the center of the river, the current is stronger than in the sides, okay? So, along my talk, I'm going to try to answer this question. And I mean, I'm going to consider this problem in several situations, and I'm going to try to give a solution. Okay? So this problem, Zermelo navigation problem, was proposed by Zermelo in 1931. And it was also considered by other German and Italian mathematicians like Levi-Civita, von Mises, Magnat, Caracedori in the 30s. So they solved the problem using calculus of variation, optical control theory, like in the talk of yesterday by Enrique, calculus of variation. But recently, in around 2000, Zhongmin Shen found a different solution for the problem. He found that you can solve this problem using Finsler geometry, okay? So, but there are many applications of the problem. I presented initially the example of a motorboat in a river, but for example, you can consider also a sailboat in the sea, or a zeppelin or an aircraft in the air. because also there is an engine and there is wind. You can consider also trajectories of sound rays in the presence of wind, or also wildfire spread modeling. I'm gonna speak later about this, because I imagine that in principle it's difficult to understand why you can apply Zermelo navigation problem to wildfire spread modeling. But in 20 minutes, I'm going to, maybe in 15 minutes, I'm going to explain why, how. And also in world animal migrations. Okay, because for example, bear migrations, well, they have they can use the currents of the winds. And these currents are more or less stable. There are always the same currents. Is this the same thing? The same thing for fishes? There is also currents in the oceans. Of course, the question is: do the animals find the solutions, the optimal solutions? Probably the answer is no, not. But they can get close. Okay. Or maybe in some trajectories they can find some kind of solution of Zermelo navigation problem. So the main goals of the talk are basically two. First, I'm going to speak about Finsler geometry in order to see how Zermelo problem can be solved using Finsler geometry. And then I'm going to explain how can you use spacetimes in order to solve a Zermelo problem which is time dependent, okay? I mean, also which is time independent, but in particular, when it is time dependent, you need a space-time to solve the Zermelo problem. It cannot be solved only with Finsler geometry. So I'm going to speak now about Finsler geometry. Let's enter in the Finslerian world. So, well, the first thing that I want to do is to define Finsler geometry, to introduce Finsler geometry. So the idea here is to focus on the length of curves. Imagine that you want to define a very general geometry in such a way that you can measure the length of curves. So what do you need? In principle, you need a norm, okay? Because if you want to measure the curves in such a way that the measure does not depend on parameterization, you need something which is homogeneous, okay? In such a case, well, the length is just the integral of the norm of the velocity of the curve, okay? So let's recall the definition of norm in analysis. Okay? In analysis, well, you take a homogeneous function. It has to be homogeneous. Here, I'm putting only homogeneity only for positive values. This is because there are very important examples in which the norm of minus v it is not equal the norm of v. This is called non-reversibility when it has this property. Okay. Well, the last property of a norm is the triangle inequality. Okay. So these are basically the three properties of a norm in analysis. So if we define the indicatrix as the points where the norm is equal to 1, and the unit ball as the points where the vectors has norm less or equal to 1, then we have the following proposition. B is convex, the unit ball is convex, if and only if the norm satisfies the triangle inequality. Okay. Probably you have seen the proof of this result sometime in your life, but it is very easy. I'm going to write it here. It's very straightforward, and it is important for the next. So, well, the proof is very simple, because if B, the unit ball is convex, then if you take two arbitrary vectors of Rn, you can consider the normalization of these vectors, and then you can take this convex combination, because these two quantities sum 1. So this is convex, and the sum of these two quantities, that this cancel with this and this with this, is u plus v over the sum of the norms. As the unit ball is convex, this belongs to the unit ball, and then you have the triangle inequality. The other way, it's, the converse is very easy, is still easier, no? Because if it satisfies the triangle inequality, then if you consider a convex combination of the two vectors in B, then directly you obtain that is less or equal to 1. So it's in the unit ball. Okay? So, well, I'm going to introduce now Minkowski norms. Minkowski, well, this is the central concept in Finsler geometry, and it's going to be very similar to the norm in analysis. The first condition is, well, is the same as in the norm of analysis. The second condition, too, is positive homogeneous. The only thing is that I don't ask that f on minus v is equal to f on v. We have some freedom. And the third condition is that the fundamental tensor that basically is the Hessian of f2, or the square of f. This quantity, this gives a tensor in every direction, has to be positive definite. I mean, this is a scalar product, and this scalar product has to be positive definite. Okay. Well, the only thing that we have replaced with respect to the analysis, norm of analysis is the third condition, this condition here. Okay. And why this? Well, this is basically, this is going to be important in order to define curvature, geodesics, and so on. Okay. So, as I said, the fundamental tensor GV can be thought as a scalar product in every direction. It's like, well, the difference between Riemannian geometry, classical Riemannian geometry, and Finsler geometry is that in Finsler geometry, everything depends on direction. Okay? In particular, you don't have only a scalar product in every tangent place, but you have a family of scalar products which depend the direction. V is the direction. Okay? Well, if you consider the indicatrix, the points where v is, f on v is equal to 1, then the fundamental tensor restricted to the tangent plane to the indicatrix is the second fundamental form of this indicatrix. Basically, the third condition before is equivalent to that the indicatrix has positive curvature. So, this is stronger than the triangle inequality, because the triangle inequality is equivalent to convexity of the unit ball. Here we are asking something more, kind of non-degeneracy, because it is not only convex, but it has the indicatrix, the boundary of this region, has positive curvature. It's a little bit stronger, but it is necessary in order to develop all the computations in Finsler geometry. Okay. So, well, this is a norm, or a Minkowski norm in a tangent space. When we want to measure the length of a curve, sometimes the norm can change from point to point. No? And this change of the norm, the fact that the metric depends on the point, it is related with the curvature. Imagine, for example, that you have a surface, a plane in R3. If you deform this plane, then it will appear the curvature. But when you deform the plane, then the length of tangent vectors are also deformed, can increase or decrease. So basically, you can think in curvature, you can think of curvature as this, as the deformation, and the change of the metric around the surface. Okay. So, well, this is finally, well, we are, in order to introduce Finsler metrics, we also have to consider, we can do it in Rn, but in general, you also introduce the Finsler metrics in manifolds. So for someone that doesn't have background in geometry, in differential geometry, what is a manifold? Basically, it's a subset that locally is like Rn, like an open subset of Rn. Okay, so and it can be identified with Rn through coordinates or parameterizations. Okay, for example, I mean, if you consider a semisphere, a parameterization, for example, is given by the projection onto the plane, onto the coordinate plane. Okay? And also, it's very important in manifolds that you have a tangent plane. At every point, you can define the tangent plane, which in surfaces is very intuitive, the idea of a tangent plane. So, well, having the definition of manifold at hand, we can define finally what is a Finsler metric. First, we have to define this object that will appear throughout the talk, which is the tangent bundle, which is the union of all the tangent spaces. Okay? So a Finsler metric is a function on the tangent bundle, on this union of tangent spaces, such that it's smooth away from the zero section. The only point where maybe it is not smooth is the zero section. And the restriction to every tangent space is a Minkowski norm. So this is the definition of a Finsler metric. So why to study Finsler metric? Well, it's the most general class in which you can study the length of curves. In a smooth setting, maybe there are other settings, but if you want to use connections, curvatures, and so on, this is the most general background. And when there is anisotropy, then you have to consider a Finsler metric. You cannot, Riemannian metrics are very isotropic. Locally, they have a lot of symmetries. So there is a there is a lack of symmetry, then immediately will appear a Finsler metric. I have to say that it was considered by some of the main geometers of the 20th century as Cartan, Chern, and Bussmann. And it also has many applications in the real world. Let's comment just about some applications. For example, Matsumoto metrics are metrics that are used to obtain the shortest path in time in the presence of slopes. Because when you go up, you go slower than when you go down. If you take this into account, then the shortest path in a mountain is not the shortest path in length. Okay, you have to find the shortest path for a certain metric, which is called the Matsumoto metric. Okay. Well, there is also, you can study also the trajectories of seismic rays when the media is anisotropic. Well, you can study Hamilton-Jacobi equation, evolution of colonies of bacteria, the Hilbert and Fag metrics. Well, the trajectories of the standard model, which is an extension of the classical standard model in physics. And in such a case, it appears some Finsler metrics, or pseudo-Finsler metrics in this case. You can also consider Finsler spacetimes as a generalization of general relativity. As I said, wildfire spread modeling, electromagnetic trajectories, and, well, the Zermelo navigation problem. Well, you can find a lot of examples in this paper together with Professor Miguel Sanchez. Okay. In this paper, the idea is not just to find applications, but to find expressions of Finsler metrics. To give examples of functions which are Finsler metrics. Well, of course, we can define the length of a curve using using this formula here, the integral of the Finsler metric in the velocity of the curve, we can define the distance between 2 points at the infimum of all the lengths of the curves between these 2 points. And this distance is not symmetric. It's not symmetric because, as I said, f on minus v is not equal to f on v. And when you reparameterize the curve in the opposite sense, in the opposite direction, in principle, the length can be different. So the distance is not symmetric. Well, geodesics are the critical points of the energy functional. But that also local maximizers of the distance. So the geodesics also are critical points of this, up to reparameterizations. Okay? Well, in fact, they are minimizers in this definition when f is strongly post-convex. Strongly convex means that the fundamental tensor is positive definite. It's the third condition in the list of Minkowski norms, in the conditions that I required for Minkowski norms. Well, what can we say about geodesics? Well, it happens like in the classical Riemannian case. In every direction, you have a unique geodesic, and which is affinely reparametrized. So, as I said, Finsler geometry has a strong dependence on direction. Okay, and well, the first tensor that we found that depends on direction is GV, the fundamental tensor. So the tensor calculus is much more complicated. In general, in Riemannian geometry, you need some connection in order to make computations. But here, there are 4 classical connections. There is not a unique connection in order to make all the computations. There is very well Cartan-Chen and Hasiguchi connections, which are connections, are not affine connections, but are connections in the vertical subbundle of Tn, which is a fiber bundle. So, trying to simplify the computations, I introduced the anisotropic calculus, which basically uses a affine connection, a family of affine connections, in order to make all the computations. You have to fix. Imagine that you want to compute something in V, in the vector small v. Then you can extend this vector V to a vector field, V capital, and use the vector V for computing, for making computations. In order to make all the things in invariants, you have to add some vertical derivatives in the tangent space. No? In such a case, you can prove that the quantities that you obtain do not depend on the extension. At the end, well, the important thing is that in such a way, using anisotropic calculus, the computations are very similar to those in classical Riemannian geometry and using Levi-Civita connection. In classical Riemannian geometry, you have the Levi-Civita connection, and the computations are very nice. Using this anisotropic calculus, at the end, the difficulty is not much bigger. In fact, you can prove that there is a Levi-Civita connection with this approach. Well, next January, there will be a course about the Finsler geometry and anisotropic calculus in Granada from 7 to 18, and so all the people that want to go is invited to go. And you can find more information in this web. Well, and also in this paper that is in archive, there is a second version just from 2 weeks ago. So let's go back to the Zermelo problem. Let's try to understand how can you use Finsler geometry, this virial geometry that I've just introduced, in order to study the Zermelo problem. Okay, well, you have to measure the time because we want to minimize the time. So how can you compute the time? Well, you know the velocity. Okay, the velocity is fixed, and the velocity is space over time. So time is space over velocity, which is this formula. So you have to integrate the dt, okay, which is basically this. Now you can define sigma is the surface of velocities. And the surface of velocities is all the vectors in a sphere of radius v0, plus the wind. W is the wind. So basically you have a translated sphere. It's a sphere which is not centered in zero. Sigma is a sphere not centered in zero. Okay? Now, the velocity has to be in sigma. So, in particular, in the direction of, well, the velocity is in the direction of gamma dot, or the velocity of the curve, but it has to be proportional to, the velocity has to be proportional to gamma dot for some lambda positive. Then, substituting here this equation, we finally obtain that t is equal to the integral of 1 over lambda. This lambda depends on the parameter of the curve, of course. But what is lambda? We know that the Finsler metric is equal to 1 on the indicatrix. And this here is the velocity, v is equal to lambda gamma dot, and then the Finsler metric is equal to 1. But then, using this equation here, we obtain that the Zermelo metric on gamma dot is equal to 1 over lambda. So basically, the time is the length of this curve with the with this Finsler metric. The Finsler metric having as indicatrix this hypersurface, the translated sphere. Okay, you can see this in a more direct way because you can reparameterize the curve with the time. If you reparameterize the curve with the time, which is the velocity? The velocity is directly gamma dot, the velocity of gamma. And then you know that C on gamma, as this is the velocity, is equal to 1. And then directly you obtain that t is equal to the integral of the Finsler metric on gamma dot. Okay? So basically, the time is the length of the curve computed with the Finsler metric. Okay, so well, let's compute this. Let's compute this metric. We know, well, in this picture you can see that this is the indicator. This is sigma. The blue circle is sigma. Okay. So we know that here in this circle the z is equal to 1. Okay. So if I consider an arbitrary point v, the first thing is I have to compute v over z on v, which is this one. And then I have to translate it. Translate it with this here is minus w. This is w. This is the wind. And this is minus. So here is in the first sphere. So its norm with g, with the initial Riemannian metric, is equal to 1. Okay? So, well, this is a second order equation in C on V. As g is a Riemannian metric, it's linear, so you can transform this into a second order equation. You can solve the second order equation, and you obtain this expression. So this is the expression for the Zermelo metric. And this is a Finsler metric, okay? And well, you can observe that this is a Riemannian metric, what is inside, more or less complicated, but this is a Riemannian metric, and this is a one form. But first, let me go back to the wildfire spread modeling. So, because in this case, the solution, how to solve this with Zermelo problem is not so obvious. But, well, imagine that there is a fire in a forest, and there is wind. So the wind helps the fire to spread throughout the forest, to spread faster. So what you do is to compute the geodesics for the Zermelo metric. And, well, you are interested in the wavefront. But in order to compute the wavefront, you need to compute the geodesics in all the directions. So maybe this is the source of the fire. You compute, there is a wind, and, well, the final result is this. Okay? Final result, the wavefront is this. Probably because in this case, the wind is this direction here. No? Of course, doesn't have to be constant. No? But probably here, it takes this direction. Okay? So this this model for wildfire spread modeling was studied in this paper by Steinbach Borgsen, and it has really many potential applications because it's very difficult to, in general, the models for studying wildfire spread modeling are very complicated because they use PDEs, and it's very hard to obtain the solution. Sometimes it takes longer than the wildfire to spread. So I think that it's very promising, these models developed by Steinbach Borgsen. So, well, the next thing I want to tell is about Rander's metrics, which is, as I told you before, the Zermelo metric is of the form square root of a Riemannian metric, square root of something, plus a one form. We can see again the expression of Zermelo metric is this one, and this is the square root of a Riemannian metric plus a one form. Okay? These metrics are called Rander's metrics because of a physicist called Ganat Randers. Okay, and they are non-reversible. Because that I said at the beginning that it's very important to consider non-reversible Finnler metrics. If you put here f1 minus v, it is not equal to f1 v. Okay, so of course it is clear that it is immediate that Zermelo metrics are Rander's metrics, but the opposite, the converse, is also true. The converse is also true because you can prove that every Rander's metric has a Zermelo expression. There is a translation of a Riemannian metric that gives you this Rander's metric, this particular Rander's metric. So, and I will say that this Riemannian metric and this vector field W, the wind, is the Zermelo data of the Rander's metric. Okay, let me introduce now the curvature in Finsler metrics. Well, the only idea that I want to transmit is that in order to define the curvature, you have to fix a vector, and then applying that contains this vector. Okay. Well, this is the formal expression, but I know as you can see, it's very similar to the Riemannian case. There is only a dependence on directions in some places, but the important thing is that is the interpretation of flat curvature. Flat curvature basically is a measure of how geodesics get closer or move away. This is true also for Riemannian geometry, of course. No? But in this case, you have to fix first the geodesic. In the Riemannian case, it depends only on the plane. But in Finsler geometry, you need to fix the geodesic. So you fix the geodesic, and then you study geodesics in a certain plane, which are close to this geodesic. So, for example, in the sphere, as the sphere has positive curvature, the geodesics get closer and closer. And in fact, geodesics departing from the South Pole meet at the North Pole. So they get closer and closer until they meet. So, well, the problem of classification of Finsler geometry of constant flat curvature is very difficult. It's much more difficult than in the Riemannian case. Because, in the Riemannian case, it was solved many years ago by Killing and Hoff. I didn't know that Killing solved this problem in 1891. And there are only three families: spheres, the hyperbolic spaces, and Euclidean spaces. Well, in Finsler geometry, it's still an open problem, but in the family of Grander's metrics, it's like 14 years ago, they found the solution in an unexpected way. They found the solution using the Zermelo problem. And basically, the solution is very beautiful, because a Grander's metric is of constant flat curvature, if and only if it is the translation, its Zermelo data is given by a Riemannian manifold of constant flat curvature and an homothetic vector field. Homothetic means, a Killing field is a particular case of homothetic vector field. So basically, a random metric is of constant flat curvature if the indicatrix is the translation of a Riemannian metric with constant curvature using a homothetic vector field. Well, so let's go now to spacetimes. Let's see how we can relate spacetimes with Zermelo problem. Well, we need some notions on spacetimes. The basic notions are that we consider a manifold with a Lorentzian metric. Lorentzian metric means that it has this index here. It has index 1. Index 1 means that we have vectors which are negative, which are time-like vectors, like vectors such that G of V is equal to 0, and space-like vectors. Okay? So causal vectors are in this cone here, okay, in here and here. So are inside this cone, okay. And a space-time is a Lorentzian manifold together with a time orientation. A time orientation is to choose one of the two cones here. There are two cones. We have to choose one of them, okay. And that's the same as to say that GVT is less than 0. So when we have a curve in a manifold, we say that it's time-like when all the tangent vectors are time-like, like, causal, spaceless, and so on. Okay, so in a spacetime, we also can define geodesics in the same way than in Riemannian geometry, using, for example, the energy function. Geodesics are critical curves of this functional. And, well, the most important curves are time-like and light-like geodesics. Time-like geodesics are describe the trajectories of free-falling objects. And light-like geodesics describe the light rays. Okay. So we will focus in a class of spacetimes. This class can be described in a product R times S like this, okay, using this expression, where G0 is a Riemannian metric on S, omega is a one form on S, and beta is a positive function on S. So, well, these are called standard stationary spacetimes. Well, many classical spacetimes are stationary, so it's a very important class. And we are going to study the Fermat principle in these spacetimes. Okay, so, well, probably most of you, no, I think all of you know the classical Fermat principle. The light rays follow the shortest path in time. But there is also a classical, relativistic Fermat principle. This principle is very old. It's almost so as general relativity. The first version for static spacetime was given by Hermann Weyl in 1917, only 2 years after the invention of general relativity. The stationary case was considered by Tullio Levi-Civita, so he worked in the 2 problems I'm working on, in Zermelo problem and in Fermat's principle in general relativity. It appears in classical books, and well, the general formulations of this principle were given by Koffner and Perlich. Probably the version by Perlich was more rigorous. So what does it say, the relativistic Fermat principle? Basically, you have to consider like curves between one point and a time-like curve. And what the principle says is that like geodesics are the curves that minimize the arrival time. So Fermat principle says that light rays minimize time. So in this context, how can you formulate this problem in this way? So basically, you consider one point, a time-like curve, and then all the light curves from here to here. So basically, like geodesics are the curves that minimize the height of here, that arrive before, basically, minimize the time. So in the context of stationary spacetimes, this is it's easier to compute, because in such a case, the time is given by this expression. You can compute the time. Given a curve, you can compute the arrival time at this. Because in this case, the arrival curve is a vertical line. Okay, the arrival curve is a vertical line. This is because, well, in this case, well, you have, as the curve is like, you have this equation, is again a second order equation. You can solve this equation and obtain this expression here. So we can define a Finsler metric. And this Finsler metric is also of Rander's time. It's the square root of a Riemannian metric plus a 1 form. Well, basically what we have obtained is this proposition here, that this is a like geodesic of the stationary spacetime if and only if the projection x, the curve x, is a Fermat geodesic with unit speed. Using this proposition, you can prove a lot of things. I put here several papers, that there are more, using this this proposition, but well, the idea is that you can describe all the properties, all the causal properties of the space-time using these Fermat metrics, because like geodesics controls the causality of the space-time. Okay. So let's go back to Zermelo problem. What happens when the wind is strong? I mean, at the beginning, I was considering just a mild wind, in the sense that I translate the sphere, but the origin remains inside the sphere. But what happens if the wind is very strong? And when I translated the sphere, the zero is not anymore inside the sphere. In such a case, well, the wind. Imagine that if the wind is very strong, maybe you are not able to advance against the wind. If you try to advance against the wind, you go behind. So this is what happens in the case of strong wind. Let me say here that Zermelo, Fermat, and Rander's metrics define the same family. So you have like two different expressions. When you have a Rander's metric, you have a Zermelo data for this Rander's metric and also a Fermat data. So basically, you can solve Zermelo problem using a space-time. And the idea basically is that, well, the intersection of the hyperplane with t equal 1 is the indicatrix, it gives the indicatrix of the Finsler metric. So this is the cone, the light-like cone of the space-time. When you make the intersection with t equal 1, you obtain the indicatives of the Fermat metric, which is the translation, of course, is the translation of a sphere. But if you want to study the case of a strong wind, is much more convenient to use the space-time. Why? Because here, when you consider this problem, there are directions where the metric is not defined. And that gives a lot of problems. But in the space-time, you have a classical space-time. So it's much easier to consider the space-time. So what kind of space-time we have to consider? Okay. What kind of we have to consider SSTK space-time. This is very similar to the stationary space-time, but in this case, this lambda can be positive, negative, or 0. And well, this allows to consider the strong wind case. So, well, again, you obtain the expression for the Fermat metrics. In this case, well, there are two Finsler metrics. Because, in fact, here, there is the Finsler metric given by this indicatrix, and the Finsler metric in this direction. There are two Finsler metrics, this and this. Okay, these indicatrix give two Finsler metrics. So, well, the situation is more or less this. Depending on the sign of lambda, you have 3 possible cases. But, well, let me just comment quickly that, well, in this case, the Finsler metric has 2 possible expressions. One is this case, I mean, this is very general, sorry. This expression is very general. But in some particular cases, you can obtain better expressions. When lambda is equal to 0, the Finsler metric is a Kropina metric, which is basically the quotient of a Riemannian metric over a one form. And in the other cases, when lambda is different from 0, there are Randers metrics. So in general, we say that F is a Randers Kropina metric. So we can solve the Zermelo problem in this very general case with a strong wind. And basically, we have an open subset such that the boundary is convex, and the wind is mild only on the boundary. Inside can be strong, but we need that in the boundary is mild. And then we solve the Zermelo problem. Okay, this is contained in this paper, a very long paper. And well, in this case, you can have also black holes. Imagine that this is a region where GKK is greater than the Killing field is space-like, or the same thing, lambda is less than 0. In such a case, basically, when you try to exit, to go out, it's impossible, because the only possible in the boundary, the only possible option is to move in the inside direction. Okay, so this creates a black hole. Okay, so we can use this more general case of Randers Kropina metrics in order to study manifolds with constant flux curvature. In fact, we have classified the Randers Kropina metrics. We have, in some sense, we have extended the paper of Bausch and Bauer-Robles-Shen about the classification of Randers metrics. This basically the same result is true for Randers Kropina metrics. Well, the last thing I want to speak about is about cone structure. So we have solved the Zermelo problem when the wind is time independent, when the wind is strong. So the last case is what happens when the wind is time dependent. In such a case, we will need a space-time, or to be more concrete, a cone structure. Why? Because basically what we need is what is a constructor? Is basically is to, well, to consider the intersection of all the rays from a point, from the origin to a strongly convex surface in a, for example, here in this region here. Okay, I'm defining a cone structure just in R times B. Okay, so well, intuitively, a cone structure is something very is very intuitive, and well, in this case, one can define likely untitled vectors as for space-times. Because, I mean, which are untitled vectors? Are the vectors which are inside in the convex region determined by the cone. Likely vectors are the vectors in the directions of the cone, of the boundary. Okay? So, in this case, we can define a Finsler space-time using the cone. Basically, we have to define a function, a positive function, which is homogeneous of degree 2, and such that the fundamental tensor is of index n-1. Is Lorentzian, the fundamental tensor. Okay? The third condition is that in the boundary it has to be 0, because if you know something about Lorentzian geometry, the cone is the region where the metric is equal to 0. Okay? So this is the definition of a Finsler space-time. And then in order to solve the Zermelo problem, you have to consider, well, this manifold here, then the cone is constructed with the maximum velocities. At every point, you construct a cone, like here. These are the maximum velocities, and then using the maximum velocities, you construct a cone. But in principle, this cone depends on time too. So, it's not just on the manifold S, but for every t and every p, you construct a different cone. So at the end, you're doing a cone structure here in M. Okay? And well, we want to minimize the time, the arrival time, and we have to consider curves with the maximum velocity. But to consider curves which at every point reach the maximum velocity is the same that to consider Lie-Light curves. So basically, what we have to do is to consider Lie-Light curves. I think that here I have a picture. Lie-Light curve from here for x to y in such a way that this curve is like. The cone is tangent to every point, to the curve at every point. It's a Lie-Light curve. So we have to find the minimizers of this. And, well, the minimizers of this are cone geodesics. Are cone geodesics because, well, this is basically, these are curves such that if you take 2 points close enough, there is no other causal curve between those 2 points. Okay? Well, and using causality, you can prove that like cone geodesics solves the Zermelo problem. Okay. So and then if you find a Finsler space-time with a given constructor, you can prove that a cone geodesic for the constructor is the same that a Lie-Light geodesic for the Finsler metric. Okay. So finally, we can solve this problem. In order to solve the Zermelo problem, we have to define the causal future. And the causal future basically is the region that you can reach with causal curves. Is basic in the universe, it will be the region that where you can arrive, because to travel throughout the universe, you can only use time-like or Lie-Light curves. Okay, so this is the region that you can reach, and basically, if you have a solution, you have a solution that minimizes the time, it has to be a cone geodesic, and if this region is closed, then you can prove that there exists a solution. So the condition in order to exist a solution of Zermelo problem in the time-dependent case is that this region here, the causal feature, has to be closed. And moreover, you can prove that in certain cases, for example, if you have a Finsler metric, if you time-dependent Zermelo metric is upper bounded by a Finsler metric which is complete, then you can prove the existence of a solution. So yeah, at the end, all the trajectories which are critical are Geodesics. So this is the solution, this is the final result, which is the solution of Zermelo problem in the time-dependent case. Okay. So, well, this last theorem is contained in this paper, which very recent paper. And well, the proof of this is uses ingredients basically uses the theory of causality and the Fermat principle for Finsler's spacetime, which is are resolved by Perlich, Volker Perlich. Just as open problems, well, we can study manifold with constant flux curvature in Finsler geometry, which is a very, very interesting topic, and also to study Einstein equations for Finsler spacetime and to study solution of these Einstein equations. So thanks a lot for your attention.
Translate the problem to a semi-Riemannian problem. Is
yeah,
that
a
Lorentzian problem, but not Finsler.
Well, no, it's Finsler.
It's Finsler. Okay. That was the.
You can use a space-time or a Finsler metric.
Okay.
In the time independent.
In the independent, but the spacetime.
Sorry, in the time dependent, with the wind depends on time, then you cannot use Finsler geometry. I mean, you can use Finsler spacetimes, but not classical Finsler geometry.
Okay, that's.